This video is about double integrals over rectangles. Before we look at double integrals, now first let's look at a single integral. If I give you a function only depend on one variable, and what do we mean by this? Single integral from a to b fx dx. And you will say, okay, y equal to fx give you a curve. Here is a, here is b. Now we know the single integral. We just say integral. Give you the area under the curve. Okay. Before we learn single integral, we don't know how to find area under the curve. Okay. I mean this area. So what area do we know how to find? Rectangles, right? So, however, this area is not rectangular area. So you cannot just use one rectangle to approximate this. So what we did is like this. We break this one to many small intervals, okay, such that this is small enough. We call this interval length delta x. Now we pick sample point, say xi, and use fxi as a height. Then you make a rectangle. Okay. So the height of this rectangle is fxi, then times delta x, which is the interval length. And this number gives you the area of this rectangle. Okay. Then add them together will give you a good approximation to this area under the curve. And this approximation is getting better and better if delta x goes to 0. Okay. So if we take a limit, let delta x goes to 0, then they will give you, that's the definition for this integral, which gives you area under the curve. Okay. If you look at this summation only before take a limit, which sample point you pick will be different, will give you different area. However, if you take a limit, let delta x go to 0, say that means this your intervals are really narrow. So which point, sample point you pick will not make a difference. Okay. So the definition for single integral is like this. If you understand this one, then we can, for the double integral, it will be similar. Okay, what is a double integral? Which is the integral for functions more than one variables. X and Y, Z. Now, we're talking about integral on rectangles. This is our domain, okay. So you go up, okay. So for the function, say, depend on two variables. Again, we know this function gives you a surface. Okay, so for the given surface, and our domain is this rectangle. Now, the single integral gives you area under the curve. So you can imagine the double, if we want to find what? The volume under this surface. How do we do that? Okay, that's a very similar question. Okay, we don't know how to find a volume under the surface, but the volume we do know how to find is what? Is rectangular box, right? Therefore, like what we did for the single integrals, we can divide our rectangle to many small rectangles, such that this one go up okay. So you can go up, you get something like that. And you pick sample point 2, say xi, yi, yj, that point is. So you evaluate, you get this point. So this height if is fxi, yj. Okay, pick just any point in this small rectangle. So fxi, yj, give you the height times base area. We call this base area, rectangular area, we say delta A, okay? Delta A give this rectangular area. So this number will give you what? The volume of this rectangular box. And add all of them together, which will give you approximation for the volume under the surface. Okay. This approximation is going to get better and better if what? If delta A, the area of this rectangle, goes to 0. Okay. Therefore, if you take a limit, delta A, which is the area of this rectangle, goes to 0, then this will give you the volume under the surface, which is definition for this rectangle we call R. Okay. Fx, y, dA. Okay. So we call this a double integral. The double integral has been defined as limit and the summation fxi, yj, delta A. Okay. You need to understand this. Fxi, yj times delta A give you the volume of this rectangular box, and all of them add together give you approximation for the volume under the surface. After you take a limit, you will find exactly volume under the surface, which is the definition of the double integral. It's very similar to the single integral we learned before. Again, which sample point you pick, if you take a limit, after you take a minute, that doesn't matter. Okay. If you don't take a limit, that's give you approximation. If you take a limit, it will give you exact volume under the surface. Okay, now let's look at the example. Now we want to estimate the volume under this surface. Okay, this surface is z equal to 16 minus x squared minus 2y squared. My rectangle here is x is between 0 and 2, so is y. Okay, now we don't know how to find exact volume on the surface. Now we're just asking approximation. Okay, now we want to approximate the volume on the surface for this situation. Okay. Now our domain here's x and y. You have a surface above this xy plane. Now say here is a 2, 0 to 2. Now we're going to estimate the volume on the surface by finding 4 rectangular box volume, then add them together. Okay. So they give us this. Here's 1, here's 1. So, and we have to give the sample point to find the volume for each rectangular box. Okay. Now we use what? Up right corner of each. We call this is R11. R21, R12, R22. Okay, imagine you have a surface above this rectangle squares, okay? And each, for example, in R11, you go up, you have a surface above that. Now, for the R11, we are going to use upper right corner. Use the function value there as a height. Then you make a rectangular box. Okay. Therefore, our volume can be approximated by, this is just approximation, okay? You only get the exact one after you take a limit. So this really is like 4 volume add together, right? This I put this way, okay? This is a full volume for rectangular box. Say V1 is a rectangular box associated with R11. Okay. V2 is associated with R21. Okay. Now V1 is what? Is the height, right? F. I'm looking at R11, okay? The height R11, you use up right corner, which is this point. Its coordinate is 1, 1. This gives you the height of rectangular box above that. Then times the base area. Okay, what is the base area? 1 times 1, so it's 1. Then plus V2. V2, what I mean, V2 here is a rectangular box above R21. And with up right corner, use the function value and the right in that corner, up right corner as a height. So F, this is x is 2, y is 1, then times base area, which is also 1 times 1 is 1. Okay. Then plus F plus F. Now I'm calculating V3, which is a rectangular box above R12. So the right upper right corner is this point, which x is 1, y is 2. X is 1, y is 2. Then times base area, which is this one, is 1. Then plus the last rectangular box volume above R22, which is F upper right corner on R22 is 2, 2, okay, times 1. And you calculate that, they give you 34. Okay. Let me give you an example. For example, if you want to find F12, okay. Our function is like 1 is 16 minus whenever you see x, replace it by 1 square minus 2, y is 2, 2 square. Okay. I'm just calculating 1. Okay, so 16 minus 1 minus 8 give you 7, right? Okay. I'm just giving you an example. Okay. Okay, so what is 34? 34 is approximation for the volume under this surface and on the rectangle 0, 2 times 0, 2. Okay. This is just approximation. Okay. How do we get this approximation? We find the volume for the 4 rectangular box above those each squares. Okay. And we use up right corner on each square. Use the function value there as a height. Now, let's do this problem again. Same thing. This time we don't choose right up corner. This time we estimate the same thing. Okay, 2 2. Also we divided it to the 4. Okay, and this time we use a middle point. 1 here, 1 here, 1 there. We use a middle point on each rectangle as a sample point. Okay, so let's call this 1 2 3 4. Okay, imagine we have what? XY. We have a surface above this square. Now we're talking about volume under this surface. Since we don't know how to find that, but we do know how to find volume for rectangular box. So what we're going to do is find 4 rectangular box volume. Okay. For the first one, we call the volume there can be approximated. Okay, by the 4 rectangular box volume. Say that the first one is F. We use a middle point. Okay, which is what? X is 1/2, Y is 1/2, right? Then times this area, times the base area is 1. Okay. Height times base area give you volume of the first rectangular box. Okay. Then plus. Okay, look at the second one. Okay, second one. Use the middle point as a sample point instead of right up corner. Okay. So the middle point here, X is 3/2. Y is what? 1/2. Okay. Times the base area, still 1. Okay. Then plus. Look at the third one. Middle point. Use F, evaluate the middle point as a height to make a rectangular box, which is 1/2, 3/2. This gives you height times the base area is 1, then plus the last one. Okay. Rectangular box above the square 4, which is 3/2, the middle point. X is 3/2, Y is 3/2. Times 1. Okay. Okay. So what you need to do, just find all those 4 numbers, plug in. You are going to see this will give you 49. Okay. Last time we got a 34. If we use middle point, we get another approximation to the volume under the surface. In fact, the volume exact one is 48. Okay. Now we got 2 approximation. The first one we use up right corner with the same 4. We divided this to 4 rectangles. The first approximation is 34. This I call this a second approximation. Okay, V2. V2 is the second approximation. Is 49. Sorry. I may made a computation error. Okay, important sense is the idea. It's a 49. Okay, what is the difference between 34 and 49? They both use same idea. Try to approximate the volume under the surface by find rectangular box volume, then add them together. We'll always have 4 rectangular boxes. Now, what is the difference? We chose a sample point. Sample point is different. One is we got a V1 by choosing up right corner on each square. Evaluate the F at that point. Okay. We find the V2 by choose sample point as a middle point. Obviously, V2 is giving you much better approximation than the first one. Okay. We use the middle point as sample point. We call this the middle point rule. Why they give you better? For example, look at the 1D case. Okay, we want to approximate the area under the surface. If you use left, for example, on this interval, you use left end point as a height, you make a rectangle like this. Then this will be your approximation area, which is underestimate. Okay. If you use on each interval, first interval, you use the right end point, make height, then you will make different approximation. This one will overestimate. Now, if you use middle point for each one, they tend to give you better approximation. Okay, now let's look at another example. This example, we want to find this double integral, square root 1 minus x squared dA. My R here is a rectangle. X is between -1 and 1. Y is between -2 and 2. Now, this time we want to find exactly this double integral. We're not asking for approximation. So to find this one, you have to understand what is a double integral. Remember, double integral has been defined as, limit summation fxi dA, which give you area under the surface. Okay. So to find this one, we have to understand what surface we're talking about here. This is a surface. Okay. So your surface here is z equal to square root 1 minus x squared. Okay. So what surface is that? If you cannot see that, let me square on both sides. I got a z squared equal to 1 minus x squared. So you can think about x squared plus z squared equal to 1. Okay. What is this? This you can think about on the xz plane is a unit circle, right? However, in the three-dimensional space, this give you what? Give you a cylinder, because y can be anything. Okay. They give you a cylinder. Now, since now you solve the z, if you only take the positive sign, they give you x, y, z. If you take a positive sign, they give you top half of that circle, okay, as cylinder. Like that. Give you top half of that. Okay. So this is double integral. Give you the volume under this surface, okay, which we know what the volume under this surface is just exactly half of this cylinder. Restrain on the here x is 1, here is -1, and we're talking about just portion of that. Y from -2 to +2. Okay. To find this cylinder, okay, the cylinder from y from -2 to 2 is what? The base area, right? This circle is pi, the volume there is pi, r is 1, okay, radius is 1, pi 1 squared. Let's give you a whole circle, we only have half of that. Then times the length of the circle, the length of the cylinder, which is from -2 to 2. So it's a 4. The length is a 4. And I simplify that to give you 2 pi. What is 2 pi? 2 pi is the volume of this half of the cylinder, which exactly is the area under the curve. That's why this double integral can be found exactly equal to 2 pi.